Assalamualaikum. My name is Muhammad KAMIL ARSHAD, metric number 231151587. I will explain about question 1. So question 1 they ask about resonant peak maintain frequency. Resonant peak maintain 7 dB per decade. Resonant peak frequency is 9.5 seconds. They can be obtained from the graph where we see the peak. And for the bandwidth, we need to see when the magnitude is 3 dB, so we need to find the frequency when the magnitude is 3 dB, which we get 16 radians per second. And for cutoff rate, we need to find the slope between 2 points, so we will take from 100 and 10, so we get negative 40 minus 6, by which we will get negative 46 dB per decade. Moving on to the next question. Given transfer function ks plus 50 over s square plus 15s plus 100, we need to draw a dot plot for the equation. So now we need to change the function into a standard form. So we will get 1 over 2k s over 50 plus 1 over s square over 100 plus 50 s over 100 plus 1. Now we need to find the components for the dot plot. So here we have 4 components: gain, simple zeros, pole at origin, and simple pole, a complex pole, sorry. So for gain, we have 20 log 1 over 2 equals where we will have 0. So pole at origin is 1 over s. For simple zero, we need to find the corner frequency 1 over t, where we have 1 over 1 over 50, where it's equal to 50. And for the complex pole, we need to find the corner frequency 1 over t, where we will have 1 over 1 over 10 equals to 10. So now we need to draw the dot plot according to the component that we have. First, we have 4 components. After completing drawing on both magnitude and phase, now we need to combine all into one line. So for 0.1, we have 20 dB, and for the first corner 10, for the decade 10, we will have a negative 20 dB per decade slope, and from 10 to 50, we will have negative 60 dB per decade, and from 50 to the end, we will have a negative 40 dB per decade. And for the phase frequency, for the from 0 to 1, we have 0 degree slope, and from 1 to 5, we will have a negative 90 degree slope, and from 5 to 10, we will have negative 45 degree slope, and from 10 to 50, we will have negative 45 degree slope, and from 50 to 100, we will have negative 45 degree slope, and last from 10 to 100 to 500, we will have a 45 degree slope, completing the line. And for the last question, based on the dot plot in part Q1b, the question asks to evaluate the stability of the closed loop system, justified by estimating the values of gain margin and phase margin. So first, we need to find the gain margin and phase margin. So gain margin, phase margin is 0 minus our magnitude response when the phase is negative 180, where we have negative 38 equals to 38 dB per decade, and phase margin is gained by negative 90 minus negative 180, we have 90 degrees. So the system is stable if the m equal to 0, when the phase response is more than negative 180, and when the phase is negative 180, the magnitude response m less than 0 dB. So we can see when phase is negative 180, our m response is negative 38 less than 0, and when m equal to 0, our phase margin is negative 90, which is greater than negative 180. Thus, we can conclude that our system is stable. So now, second question asks, if the value of case increases 20 dB, evaluate the system stability. Justify your answer by sketching the resultant dot plot on the same graph of part Q1 dB. So now, after we have drawn the summing up line, so we now need to add we need to add 20 dB on all points. So we will add 20 dBs on every points, maintaining the slope, just increase the points by 20. So when we add the 20, the magnitude response m will be equal to negative 18, which is still less than 0. Thus, we can conclude that the system is still stable.
Hello everyone, I'm AISSWARYA. For this question, I'm given an open loop control system with the transfer function given as Ts, where k equals to 4. The task is to analyze the system using the dot plot and determine the stability, gain margin, phase margin, bandwidth, and the effect of increasing gain. First, transfer function is normalized into standard dot plot form. The overall gain is 1.6, which corresponds to the plus 4.08 decibels. System has a pole at origin, a simple zero at 10 radians per second, and a quadratic pole at 5 radians per second. These components determine the slope changes in the magnitude plot and the phase behavior of the system. Using these poles and zeros, the both magnitude and phase plots are drawn as shown here. The pole at origin contributes a minus 20 decibels per decade slope, The quadratic pole further reduces the slope to minus 40 decibels per decade. The simple zero increases the slopes and adds positive phase to the system. From the board plot, the gain crossover frequency occurs at approximately 1.4 radians per second, giving a phase margin of about 60 degrees. The phase crossover frequency occurs at around 11 radians per second, resulting in a gain margin of approximately 30 decibels. Since both margins are positive, the closed-loop system is stable. The system bandwidth is approximately 2 radians per second. When the gain is increased by 30 decibels, the magnitude plot shifts upward, reducing the gain margin to about 2 decibels. So the system remains stable, but it becomes more oscillatory and less robust.
My name is DECXY Vincent, and I will be answering question 3. Okay, so for question 3A, Roman 1, the most stable system would be system 1. Because the endpoint for system 1 is at the positive real axis. For question 3A, Roman 2, for S1 it has 0 integrator because the endpoint end at the positive real axis. For system 2, it has 1 integrator because the endpoint fell at the 90-degree plane where omega approaching infinite. Okay, so for question 3B, we are required to draw the NQuest plot. Okay, so to answer this question is, for the transfer function, we have to replace the S with J omega. And then the second step is to identify the real part and imaginary part. After that, we have to evaluate by finding it by replacing omega with equal to 0 to get the low frequency, and then we evaluate to find the omega equal to infinite. For the result, we will get the starting point and ending behavior, and then we plot the NQuest plot that is sketched based on this key value. Okay, so for question 3C, based on the NQuest plot for the system, it lies on the right real axis, so the closed loop system is stable. This results in infinite gain margin. The gain can be increased, and for the phase margin, it is in the positive side, so the system can tolerate in decreasing the phase lag. Okay, so for question 3D, the new system make a phase lag at negative 90-degree plane where the gain margin approaching infinity. This make the phase margin to be reduced. Therefore, the stability also reduced.
For question 4, part A, Roman 1, we are asked to determine the number of integrators in system S1 and S2 using their Nyquist diagrams. From the Nyquist diagram of system S1, the plot starts at the origin and ends at a finite point on the positive real axis. This indicates that the magnitude remains finite when the frequency is 0. Since there is no pole at the origin, system S1 has no integrator. For system S2, the Nyquist plot moves downward into the complex plane as the frequency increases. This behavior indicates the presence of a pole at the origin, which represents an integrator. Therefore, system S2 has one integrator. For question 4, part A, Roman 2, we are asked to determine which system has better stability. By comparing the Nyquist diagrams, system S1 remains further away from the critical point compared to system S2. Being further away from the critical point indicates larger gain margin and phase margin. Therefore, system S1 has better stability than system S2. For question 4, part B, we are required to sketch the Nyquist plot for the given system. To obtain the Nyquist plot, the frequency response is analyzed by identifying the real and imaginary parts. Key values are considered when the frequency is 0 and when the frequency becomes very large. These values determine the starting point, ending behavior, and overall shape of the Nyquist plot. For question 4, part C, we are asked to evaluate the stability of the closed loop system. All open loop poles are located on the left side of the complex plane. So, from the Nyquist plot, it is observed that there is no encirclement of the critical point. Therefore, the closed loop system is stable. For question 4, part D, an integrator is added to the forward path. This introduces additional phase lag, causing the Nyquist plot to rotate downward and move closer to the critical point. As a result, gain margin and phase margin decreases, making the system less stable. For question 4, part E, a 0 is added at -2. This introduces a phase lead effect, shifting the Nyquist plot away from the critical point. As a result, gain margin and phase margin increases, making the system more stable.